Okay, so let's start for our second talk. So it's my pleasure to introduce academic part of our meetup. So this is Ali, and yes, you can see a very, very nice introduction about him. The key thing is that he's doing right now a PhD with LMU, with one of the top chairs for NLP and for relevance research. And today he will talk actually about his PhD topic, and he's wrapping up his PhD very soon. Yeah, so retrieval, long context and multi-turn interactions, and it's kind of like a combination. It's a nice example, yeah, how you can apply different theoretical findings with engineering approaches. So yeah.
Right. Thanks, Darina, and thanks Munich NLP for having me here. And yes, I'm Ali, and I'm nearly starting my 4th year in my PhD, which is basically in memory-augmented LLMs. And here today, I'm going to discuss about benchmarking memory and LLMs, retrieval, long context, and multi-turn interaction. Okay, just as a background, I mean, LLMs are everywhere. I'm pretty sure everyone knows about that. And they're kind of the center of all of our systems right now. They are the processing unit. And they get a lot of different sources of input. Like you have these short-term inputs, like just a query that you just write into your chatbot. Sometimes you have like large or like distributed information. Sometimes it's like a search or something like a large book. And sometimes you have external knowledge. So you want to have some sort of tool. You want to do some like interaction, agentic stuff, and all that. And all of this means you're feeding a lot of information, sometimes short-term, sometimes it should be persistent. And this would bring up the requirement of you need some sort of memory here. So here we're showing 2 types. I mean, I'm sure there are a lot of new other architectures like state space models and all that stuff. But the ones that are more frequent right now are the context window, where you could talk it as a short-term memory, and retrieval plus the context window or a knowledge base which helps and retrieves relevant information and give it to the LLM. So based on these 2 categories, we set to long context and RAG, and again, short-term or long-term. And in my whole slides, I'm going to discuss about 3 settings. One is the setup where you have all your documents, feed them into your context window. So it could be like upload a PDF or a multimedia file or whatever, and a user query. So you feed in the whole context window, the whole input of the LLM with the input that you're giving, the query, the documents, and then you get an output. Another setting would be like those setups that you constantly chat with your chatbot and never open up a new instance. So you have like input 1, you get an output. Now, when you append your next input, like input the next chat you have, now you have the new input of the LLM, which gives you the next output. And all of this all together will form a long stream of context, again, for the nth input that you give to the model. So again, you have a multi-turn interaction setup. Now, there is another case where we have retrieval, where you could also have a shorter form of context window, but with the help of a retrieval model. So you have this retrieval format, all documents. The query also has a play here, and then you just retrieve the relevant info and feed that to the input prompt. Sometimes it could be long, but usually this could be a technique to use less tokens in the context window. So we have 2 questions here. Number 1 is, how well do LLMs perform in longer contexts, either in single or multi-turn interactions? And the second question would be, how robust are retrievers to diverse query types in RAG systems? So as I mentioned here, you have this retrieval, which could impact your final output because it impacts your input here. So again, we have the retrieval question and the long context question. On that, I'm going to rifle through some of my work, quick view, but in the end, you could check out my LinkedIn or my Scholar anywhere to check out each of these detailed benchmarks on each of these setups. Now, Nolima is the paper that I had with Adobe during an internship. When it published, it made such a noise because we also one of those people who bashed on Llama 4 on their poor context window. And basically, it's based on the very famous needle in a haystack setup, but I didn't like one part of it. And who actually knows about the needle in a haystack benchmark here? Okay, quite a few. So the general idea is pretty simple. You have the haystack, which is some concatenation of long text, and then you have a needle, which would be some fact placed inside the text, and then you ask a question that is relevant to that needle that you place inside the context. So here you have, like, what is the best thing to do in San Francisco? And based on the needle there, it should answer, like, sit in Dolores Park on a sunny day, whatever. And you could place the needle in separate depths, like in the beginning, in middle, in the end, and you can also vary the context length. In the end, you get some sort of score. Now, the thing is, a lot of these modern models are kind of saturated on these scores. So you could see here, this is also an old result on GPT-4, but even like these models, which are also old by now, are pretty much saturated the results on long contexts. So the thing is, our hypothesis was maybe because there is a large exact match, like literal overlap between the query and the needle that you're placing. The attention might get a clue where to look at. So we also checked how much lexical overlap we have. This is basically a Rouge score which says how much overlap we have between those facts and the queries. And you can see a lot of these benchmarks, the prior benchmarks, have this kind of overlap. Now, in Nolima, we designed the benchmark intentionally where you could solve the problem, but without any type of lexical overlap between the query and the placed needle. How we did that? We also have the same setup, but instead we have a needle. Let's say Yuki lives next to the Zempa Opera House, and if you ask the direct question, this would be the classical format of needle in a haystack. Now, if you make a little twist, and by the way, the Zempa Opera House is in Dresden, and I ask which character has been to Dresden, then the answer should be Yuki. Now, the question you might ask is whether the model knows that intermediate fact or not. We'll get to that. But also, you could also have two-how questions. So you could say, been to the state of Saxony, for instance. Now, one thing here is that we built a lot of different set of needles and a different set of queries based on this format, and also did a lot of cleanup to do because we want to make sure like there's no character that has been to Dresden or state of Saxony inside that haystack already. So we filter them out, and then we come up with the results. Now, first of all, we have no saturation now. But also, I have to mention these base scores. What do they mean? Is basically saying that on a short context, the model is able to answer that. And remember, we wanted to make sure that they know those intermediate links. This is kind of proof. So the model does understand that intermediate link, but can handle the task on longer contexts. So we also tried this because it got the fame and so on. Adobe also kind of post-funded the benchmark after I left Adobe. So they also tried out newer model at the time. GPT 4.1 came out saying, oh, we aced the needle in a haystack test. And then we said, oh, not really. And there are a lot of evaluation and analyses here, and also more even updates on the benchmark. You can check the GitHub. I think we have Gemini 2.5 Pro as well. But the main thing I want to mention is actually here, the reason of what's going on here. Remember the literal matches? The attention mechanism is actually very much built for this finding and recalling exact matches within the text. But when there is a hop, when there is this like implicit reasoning involved, then the harder the implicit reasoning, it would be harder for the model to know where to look at in general. For instance, here is an edge case where we have the question, the needle at the very end. And after that, you have the question. So literally, they're back to back. And still, the performance is less than 20%. So in 32K, so you have so much noise tokens, the model doesn't know where to look at, even though the needle is just like next to the question. And also, I skipped these, but we also tested out reasoning models. Reasoning helps, but to some extent. Sometimes it could like reiterate, oh, I've seen the Zempa opera somewhere, and that reiteration brings up an exact match between that reasoning trace and the query, and then it builds up the answer. But if it doesn't have any sort of clue, then again, you'll have a problem. So that was for the single turn in interaction. For the multi-turn, we have this recent paper, which I'm going to present in Morocco in a month from now, and it is about persona consistency. Now, the question is, what happens when, like, we could have a persona, like, let's say we could ask a model, act like Albert Einstein. So we're asking what happens when personas must be sustained, like, for long interaction. Like, if you have that system instruction in the beginning, would it sustain that amount of interaction? Now, we generated a basic data set based on like dialogue prefixes. What we did was like taking other data sets, seed data sets, which are collected on dialogues and etc. And then for like, we passed in some multiple rounds, and then in the middle, we suddenly ask either a like persona, a general instruction, like a general, like let's say, what's the capital of Germany? And that's a general instruction in that case, or a persona instruction, like what do you like? It's about the persona. Or safety instruction. So it could be a safe or unsafe instruction, and we ask and see how the model reacts. And in the end, we evaluate. Again, what we've seen here was that the persona case, the blue lines, you could see they kind of drift over conversational rounds. So if you ask persona-directed questions, so basically ask about the persona itself, it kind of reminds the model what persona is. But if you don't, if you just ask goal-oriented questions, general instructions, general questions, it kind of drift off. And the other way around also, we've seen that as the fidelity kind of drops, the model kind of reverts in terms of instruction following. So they kind of have this return to factory settings as the conversation goes forward and forward in terms of even instruction following. So this was the part for the single and multi-turn interaction. So you could just the general picture here, they're not that much robust in terms of long context themselves. So I would say the million tokens and all that kind of claims should be you have to check them with the proper evaluation. Now let's go for the retrievers. Another paper here, which we presented at ACL. And a lot of these retrievers are usually benchmarked with like some retrieval benchmarking data set like NQ. And you see how the recall or NDCG, like literally the ranking is turning out. But the problem here is you don't have any feedback of what's going on underneath. You don't know what's going wrong about the model. So since my background was interpretability, this was like, okay, could we use those interpretability background and bring it over here on retrieval and see what's going on? So we tried to kind of decompose the representations. There are lots of interpretability methods for that. And we decomposed the representations on the document and the query side. And we just figured out, okay, there are some sort of biases inside. Like we have a positional bias. For instance, sometimes when the relevant entity appears in the beginning of the document, it kind of pushes the rank on a higher rank, so you get a higher score, retrieval score, than the ones that the similar entity shows up later on. Or sometimes you have repetition bias. So if the entity that is repeated in the query appears a couple of times in the document, again, you get a higher score. And also sometimes brevity is also a case. So this document is longer than this one, while this one is the correct one. And you could see it's getting a lower score as well. So all of these biases could have play here. That's why we generated a data pipeline. So we have this data set. And based on this data set, we tried to figure out which of these biases do really exist or not. And based on the position bias, literal bias, brevity bias, repetition bias, and all against answer impact, whether the answer is really there or not. In the end, we want the document to have the relevant answer with the query. So what we've shown that, okay, these biases exist, different models, different amount, and also they could have compounding effects. So sometimes all these, you could compile a set of data set with all 4 biases or a set of biases, and then you would have a catastrophic event. So you will always get an accuracy of 0%, like choosing the incorrect document in the end. And you can see also it impacts the downstream RAG impact. So if someone, an attacker, like attacks your knowledge base, or if you're using an open knowledge base like web search, basically, then you could have a poison doc. So if you have a clue what retriever a system is using, then you could build up documents online. So it tailors to that retrieval method, and then it retrieves up and come up into the system that you didn't really want to use them. And last but not least, on this 4th paper, which is also presented in EMNLP this year, which is also benchmarking on retrieval, but more on implicit facts. Now, I've shown you some biases in retrieval. This is more like how would it impact on use cases and query side. So as a TLDR, we have a lot of data sets that try to build up difficult multi-hop queries, like who is the grandfather of Leonardo DiCaprio? So you have to first figure out who is the father and the grandfather, and then these multi-hop reasoning. So you have a compounding effect on the query side. And there's a lot of benchmarks on that. There are RARB, there is Bright, there are lots of benchmarks on that side. But we thought, okay, do we have any sort of benchmark that is on the other way around? You could have a clear query, like who was visiting a museum on such a date, so a very clear point. But the document might not state the exact fact explicitly. So for instance, you might have a timestamp, and this here says, Maeve says, when I visited the Smithsonian National Air and Space in Washington, D.C. 7 days ago. So 7 days ago would be the 6th of October, so this is the correct answer. But this one has a different timestamp from 5 days ago and gets a higher retrieval score. That's what we don't want. But the problem is it's on the document side. The reasoning part is on the document side. So it's nothing that you could handle during inference. So it's not an easy solve for this for now. But we also tried different types of implicit reasoning. So you could have world knowledge, like the Dresden case. So you have a place and it's located somewhere, and we ask about the place. Arithmetic, sometimes you have arithmetic going on, sometimes it's involved money, and you could have that accounting documents and so on. And temporal, which is like this example. And also, the problem is, this could also impact RAG performance as well. So we tried out this test. First, as a sanity check, we just placed the only document inside, asked ChatGPT or GPT-4 to answer the question, and it did pretty well when you have just one of the correct document, of course. But in RAG, usually you retrieve a top K setup, K 10, K 30, because your retriever is not retrieving the exact relevant documents. So what we did was saying, okay, if we have 10 documents and 30 documents, and making sure that the correct document is inside, so we just add 9 other noise or 29 other noise documents, then you can see the performance starts to drop. And it means that even the model cannot easily solve these implicit facts if you just handle all the implicit facts to the model. So back to these questions. Single, multi-turn interaction, long context, we've seen their flaws. Rack systems, also flaws. So is the really answer here is not good? There is no one-size-fits-all solution here. I mean, yet. But there are a couple of solutions that you've seen here and there, like hybrid search, agentic retrieval, knowledge graph LLMs, and query expansion. And by the way, on the last task, like we developed our own case with both document expansion and document aware indexing, where you have this indexing where you are aware of what are inside your documents. Does your retriever know about them or not? But in the end, I want to end up with this message that you've seen a lot of papers here and there. Choose an evaluation data set appropriate to the task, and then evaluate your target system. So you had all those solutions here and there based on your needs, and a lot of benchmarks are available. Evaluate and see whether it works for you or not. Thanks for your attention, and I'm open up for questions.